Hey kids, today we're gonna start talking about lighting, alright? Lighting. Like so. Sometimes incorrectly spelled lightning, but no, that's lighting. So there's a few compartments to the lighting model we're gonna do. The first one is deferred. Deferred lighting. And deferred lighting is the part of the light source hitting straight on. So if we have the sun here, I'm just gonna talk about the sun because it makes it a little bit easier. We're gonna assume all the light rays are coming down at exactly the same angle, right? So they're all coming parallel to each other. It's because the sun is so far away. And then we have some surface here being lit. And when we talk about diffuse lighting, we're wondering, okay, if we think about some area, so let's say this area here, of light rays or photons, how many of those are hitting the surface versus are being, missing the surface? So if the surface is completely perpendicular to the light source, then, we will say 100% is hitting the surface. But if the surface is slanted like this, like so, and we still have the light rays coming in like this, let me draw the same area, like so. Then the same amount of rays or the same amount of photons are actually lighting up a larger surface area. Can you see that this area here, like this line here, is much longer than the area of the line here? So that means the more slanted the surface is compared to the light rays, to the photons, the more the light is getting spread out on the surface because it has to cover more area. Right. So that means the more the surface is tilting away from the light rays, the more the light is being spread out and it becomes weaker on that surface. So, the more slanted it is, the more dark it's going to become. Until, of course, it's completely parallel with the... Let's take down the mic here. Until it's completely parallel, in which, no light rays are hitting this surface. They're all sort of missing right this. Right, so the light rays is going right through. So this is called diffuse lighting. And the way we calculate what the diffuse lighting is by comparing the light rays to the normal of the surface. So if we look at the normal, here is pointing straight up. And so I'll type that as N, and I'll denote these light rays as L. Make a little arrow to denote that this is a vector. So we have the normal vector N and the light vector L. And to find out how much light is hitting the surface, we sort of compare those two and see if N is pointing straight towards the light source, the light vector and the normal vector are sort of, completely opposite, then it's receiving maximum light, as many photons as possible are hitting the surface per unit area. And then it's as the normal vector starts pointing away, so to N, and then L. As the normal vector starts, pointing away, then less light is hitting the surface. It's being spread out more. And then, of course, as it becomes parallel, or, the normal vector becomes perpendicular. So here's the N, and then L is pointing this way. As the normal vector becomes perpendicular like this, then no light is hitting the surface. And of course, we could talk about the example where the normal vector is pointing away, but that would mean the surface is facing away from the light source, right? And that means, nothing is hitting it because it's being blocked by the other side of the surface. Because we sort of assume that every side here has two sides, or every face here has two sides. So how do we calculate it? Well, the dot product does something very similar, right? As two vectors are parallel, I'll draw two vectors here, so A and B. As two vectors are parallel, their dot product is going to be 1. So A dot B, when they're parallel, is equal to 1. And the dot product when two vectors are parallel but opposite, so A and B, then in this example, then A dot B is going to be equal to -1. All right? So it's 1 when they're parallel facing the same direction, and -1 then when they're parallel facing the opposite direction. So this is kind of almost what we want, but we want the other way around. So the way we'll do this is just flipping one of these vectors. So we'll flip, for example, the light vector. So if we take the formula here, n dot minus L, so that's going to be our diffusion formula. Then in this example here, where the normal is pointing exactly away from the light source, from the light direction, here we'll get 1. So that's going to be 1 diffuse. And here, when they're facing sort of a little bit off, or a 45-degree angle or something like that, we're going to get, 0.7 or something. And then as it's pointing perpendicular to the light direction, we're going to get 0. And then, if the normal keeps rotating around, so it's actually facing away from the light, it will get minus values, but we will just treat those as if they are 0. So that's diffuse lighting. Diffuse lighting handles how much the light source is directly hitting the surface. Cool. So let's code this. So first of all, I'm going to make some new shaders, just so we can start fresh. So I'm just going to make light.frag and light.vert, like so. And let's hop into Visual Studio here. So here we should see, there's light.vert and light.frag. So let's hop into vertex shader, start writing that. So I'm just doing the main function here. So we want to define some inputs. So our inputs is going to be our position and our normal and our texture coordinates. All right, and we want to be good citizens and decline these layouts so we never get surprised by which attribute index they are assigned to. So I'm just going to do like so. So the attribute index is always the same. Like so. Then I'm going to define some uniforms. So I'll do the model and the view projection. Like so. And then I'm going to define some outputs for the fragment shader. So we're going to output the normal. So let's do that, because we want to check that against the light. Cool. So we're going to output to GL position. That's going to be U view projection times U model times spec 4 A position 1. So that's just what we wrote last time in our last shaders. And then we're going to output the normal to the fragment shader. So that's going to be our vertex shader. Looks pretty good, I think. Let's do the fragment shader. And now I wish I could split the view, but I can't without crashing. So that sucks. So we're going to do the vertex shader, the fragment shader. A little bit loopy. So we're going to define some inputs. We're going to do f normal. Again, we have to make sure the type and the name are the same as with the vertex shader, or we're going to get a linker error. So keep that in mind. And I'm going to define some outputs here. So we're going to do out vec 4o color. And then I'll make my main, and I'm just gonna set the O color to be F normal and then 1 for alpha. Because remember, our color is vec 4 and normal is vec 3, so I have to add the alpha here to make sure the vec 4 is actually completely filled. Let's see what happens. Actually, that's let's just recompile. I don't think that should be what we see, because I haven't actually assigned the shader to anything yet. So there we go. Okay, so we still got hairy boy. All right, so let's actually assign to the monkey then this new shader. So here for mat 2, which is the monkey material, I am gonna use the light instead. So light vert and light frag. Ah, cool, there we go. So now we're using the light shader here for the monkey face. I'm actually gonna make the window a little bit bigger. There we go. All right, so now we have the normal. So this is the normal of the surface. And now we need to define some sort of light direction, all right? So I was talking about the sun, right? Which you can see as a directional light. You know, it's actually a very, a very big point light, but since it's so far away and it's so bright, it's, you know, essentially like all of the rays are parallel. And that's what the directional light is, you know, simulating. It's simulating a light source that, you know, infinitely far away and infinitely bright. So it distributes its light as a ray that's constant, and it never goes down in strength, no matter the distance. So that's a directional light. So let's define one in the shader then. So I'm going to light frag, and I'll make some uniform here, and I'm gonna make a vector 3 uniform, and that's gonna be our U direction. Excuse me. Directional light. There we go. So that's gonna be our directional light vector. So to get the ambient, excuse me, to get the diffuse lighting, so we'll just do diffuse lighting. We'll do what we said here. We'll dot the normal with the negative light direction, right? Again, the negative is because we want it to be 1 when they are facing each other, while the dot product gives 1 when they're exactly parallel. So we just want to flip it. Normally, the dot product gives -1 when they're facing each other. Whoops, sorry, I bumped the mic. So that's why we do normal dot the negative light. So we'll do float diffuse. Diffuse is equal... is equal to, oh my god, struggle bus of a line to write. So diffuse is equal to dot, and then we'll do F normal with -U directional light. So that's going to be our diffuse value. So that's a floating point right now. So that's just going to be what the value of the diffuse is. So let's just set that as, you know, RGB for now. So we're just gonna set the red, green, and blue to be the diffuse value. So let's see what happens. It's black, so that's not what we sort of expected. But of course, we haven't set the U directional light to anything yet. So we're gonna have to make sure to do that. So let's hop on into main, and I'm actually gonna put that in this render data struct. So in the render data, I am also going to include the light sources. So I'm going to include here directional light as a vector. So we're sort of sending that into every draw call, because when we set everything, we're going to set lights. So we're going to, in the material, also set U directional light to data. Like so, and I don't believe we've done a material set for vectors. No, we don't. So we're gonna make sure to set to do a material set for vector as well. So I'll just copy this one. Instead of mat 4, I'll do vec 3, and then copy the definition here. Just do a vec 3. And then instead of GL uniform matrix for FV, we're instead gonna do uniform 3FV. So then we'll give the value pointer like so. So that sets a 3 float with a pointer, and then we're giving it the pointer to the vector 3 here. Cool. So now we got this thing. That doesn't look great. Don't know what's going on there. But of course, I haven't set the directional light yet, so I actually don't know what this even is. It's probably just garbage, honestly. I think it's just a huge vector in just some random direction. But it kind of looks lighty, like, you know, if it's like a really strong light. So let's set it to an actual value. So I'll do directional light is equal to... So I'll normalize it, because we want it to be normalized. And then I'll set it to vector 3. I'll do -1, -1, -1. Yeah, let's do that. So that's gonna be, you know, left and then down and then into the screen. So it's gonna be like diagonally into the screen, downwards. You can of course set this to any direction you want. Ah, there we go. This looks better. So now you can see that we have the direction light coming from sort of this direction, right? Because this face here is sort of very lit up, and his eyebrow here is very lit up, because those are the surfaces that are facing directly towards the light. And then as the surfaces get more and more facing away from the light, they are turning more and more gray or dark or black. And then, you know, if I go over here where he's totally facing away from the light, then they are all completely black. So that's, you know, as it crosses this 90-degree angle where the light's coming from this way, then it turns to completely black, because that's when the dot product turns negative. Cool. Let's put it on the cube and the ball as well, actually. So I'll just set it to be matte 2 by default. There we go. So now in the sphere here, you can see this divide here where, you know, they go from facing towards the light to facing completely away from the light. I wonder if I can make this smooth as actually. Maybe I should. Either way. Doesn't matter. And the cube looks kind of boring because these three faces are all equally facing the light. So that's why they have exactly the same color, which is kind of, you know, kind of boring. So that's, luckily we have some more interesting objects to look at. Cool. So now we can make the light sort of, you know, move around maybe to see how that looks. I'm actually going to make it spin. All right. So I'm going to make it look downwards, but then spin sort of around like this. So we're getting the light coming in from all angles. So I will make that sine of time -1. It's downwards, and then cos of time. So now it's going to spin around on the x and y axis, but still point downwards on the y axis. And there we go. That looks pretty cool. So you can clearly see on the sphere here where the light is coming from, right? You see this, like this bright spot here, and that's, you know, directly facing the light source. And the monkey here looks pretty cool. Maybe we got like a dramatic angle going. Let's just go like directly upwards. Let's just do like 0, 0, 0, 1, 0. So now the light's gonna point like directly upwards. Maybe he will look very dramatic. Yeah, there we go. I'm proud to take your soul. How nice. This looks pretty cool. It's like banded now. Looks neat. Cool. So let's get back to a simpler angle. Actually, I'm just gonna. Oops. Let's go back to the -1, -1. Like so. So, you know, another way to get, you know, a more dynamic look at this guy is to, of course, spin him around, right? Because if we spin this guy around, we should get, you know, different surfaces of him hitting the light differently. So let's do that. So I'm just gonna take this render data here for the monkey, and I'm gonna add a rotation to it. I'll write it like this. This is the same way as doing an identity matrix. Whatever. I'll angle, so I'll just do time, and then I'll rotate him around the y-axis. Okay, so that's kind of weird. So it looks like the light, like right now it should be lit here, but it seems like the lighting is actually static on him. You know, you can see on the ball, like the light is not moving. It's only the monkey head that we're moving right now, but still the light seems to be moving on him, or it's like constant. So why is that? Well, if we go back to printing the normal for a sec, so I'll just comment this out and print the normal. We can see that the normals don't change. You know, the normal, this one that's pointing in the Z direction, you can see that it's always pointing in the Z direction. It's normal, even though, you know, the actual face of him is not pointing towards the Z direction. Rather, when, like right now, for example, this blue should be black, like this black here. And this, you know, should also, every point of him actually should be changing when it's rolling around. So what's going on? Well, you know, we're feeding in, you know, just the straight normal from the mesh data. So that's, you know, the normal that comes in from loading the mesh from file. But that's going to be the normal when it's, you know, sort of standing upright, when it has no transformation, when it just on its own, basically. But that doesn't mean that the normals won't update when I'm rotating the mesh. Like, the mesh has no idea I'm rotating. It doesn't care. It just gives the normal. So we have to ourselves also take this into consideration for the normal, so that when we transform the mesh, we also transform the normal. So how do we do that? Well, we want to transform it from, you know, sort of mesh space into world space, you know, like in world, how is it rotated? But what if we look at the monkey head as itself, like, because we're doing this all the points, right? You know, we are applying the model matrix here. We are applying the model matrix to all the vertices on the mesh, and that's what makes it spin around, right? But what if we just did the same thing to the normals? Like, if we just apply the model matrix to the normal, if we rotated the head 90 degrees, then the normals should also rotate 90 degrees. So that means they will point in the right direction, right? I think that feels pretty logical. Let's try it. So I will multiply a normal with the model matrix. Let's see what happens. Oh. Okay, ambiguous overload function reference, blah, blah, blah. So, okay, so that's not good. So the problem is that we're trying to multiply a vector 3, or a matrix 4 rather, with a vector 3, and that's just not sort of allowed in OpenGL. So I will have to convert this to a vector 4, like so. And I have to give the W component, and again, like I said, it's gonna be 1, like always. Let's see what happens. Oh, include the cast from vector 4 to vector 3. Oh yeah, because we're trying to set a vector 3 to a vector 4, because umodel times vec 4 will return a vec 4. So we're trying to set f normal to a vec 4. So we're gonna have to get just the xyz component from this, like so. So I'll convert it back to a vector 3, sort of discarding the fourth one. Ah, great. Okay, so it works. So here are the normals. They look kind of weird though. Like, this side is not red. Like, the blue works and the green seems to kind of work, but his side of his head should be red because it's pointing in the X direction, but it's not. It's actually kind of black. So that's weird. And whoa, what the fuck? Okay, what's happening here? This guy is like orange. And this side should be black, but it's completely red. So why is that? Well, we can see that the cube in the middle, he looks correct. Like, he's like, you know, red, green, blue. So let's use the basis vector. So that's sort of what we expect. So why are these getting messed up while the cube is fine? Well, that's because this U model matrix contains translation as well as rotation. Which means that if we're translating the ball 2.5 units to the right, that means we're going to translate the normals as well. And translation in, you know, layman's terms means essentially adding. So we're adding a vector to this when we're applying the matrix. But that doesn't really make any sense when it comes to normals, because normals are supposed to be normalized, right? So rotating a normalized vector, that's fine. It will just stay normalized. The size won't change. But if we translate it, it's gonna change size, but it's also gonna be like, okay, what's gonna because you know, if we have some normal here, so that's our nice normal. If we add, you know, our translation vector, this, let me call that t, then, you know, it's gonna be this plus a little bit more, I think, plus this. So our final vector is gonna look something like this, right? So this vector here is the n plus t. If that's n and that's t. Oops. And that doesn't really make any sense. Like, the direction has changed. Like, this n plus t is clearly pointing a different direction than our n. So our norm has been fucked, but also the length has been changed. So even the length is also fucked. So we have to sort of disregard this translation. We use only rotation, no translation. So how do we do that? Well, there's a hacky way that I'm actually going to teach you guys. It won't work for everything, but it will work for this. And that is to actually disregard what I've been saying before, saying that the W component should always be 1. In this case, in this one case where we're multiplying by a model matrix, the 1 at the end actually decides how much is getting translated, right? So if we do a W component of 1, that means we apply 100% of the translation. So if we actually set that to 0, that will remove translation from the multiplication. It won't add that translation vector. So if I just do 0 there, now it actually works. So now we can see, you know, this is green, this is blue, this is red like it should be, and then it's just fading in between them. And if I look in this direction here, it's black, and the same thing for the monkey. So now the normals are looking okay. They are being rotated like the mesh, but they are not being translated like the mesh. However, there's one more caveat to this, and that if I scale, so if I go in here and let's say we take the sphere and we scale it, I'll do identity matrix, and then we'll scale it by 5, so we get a huge sphere. Oh, okay, there it is. Whoop. Okay, then we see that these values clearly are getting quite warped. Like, there's this huge section here that's just completely white, while before it was scaled, like when it was small, then it was fading in between sort of red, green, and blue, never actually completely reaching white. So, and you know, the same thing is happening here where it's scaling the normal vector. So instead of having n here, it's becoming 5 times as long. So, you know, the normal vector ends up being this long. So that will also, you know, screw with our math for here, because the dot product, we're using the dot product, and the dot product is using scale of the vectors to get its value. So the diffuse, instead of being 1, it's gonna be, you know, 5 or something when they are facing each other. So what I'm gonna do is actually gonna normalize the results as well. Normalize. So we're gonna since scaling never changes the angle, we can safely normalize it back to 1 without losing any information. So now if I look, okay, this looks better. So now it's sort of cleanly fading between the two basis vectors. So now our formula can handle scaling as well. However, there is one final caveat that is not covered by this, and that is non-uniform scaling. Maybe I can find a picture of this. I think there should be a good... Yeah, here it is. So I'll just open this. So here you can see the problem. If we have a sphere, it works fine. But if we squash down the sphere, all the normals will be non-uniformly squashed as well. So you get this shape, where you can see this normal here is getting squashed by the same amount as the sphere. But this surface is no longer pointing this way. It should be pointing more upwards. So here you can see a correct normals for the scaled sphere. You can see that the topmost normals should be pointing more upwards, and the downwards should be pointing more downwards than they do by just applying the scaling matrix. So the result is, okay, this hack works, but it will look weird with non-uniformly scaled meshes. But I'm actually gonna say that's fine, and I'm just gonna say that we cannot do that, because that's a thing that you shouldn't do anyways. You shouldn't non-uniformly scale anything if you want it to look nice. So I'm gonna say that's a job well done and call it a day. There is a proper way to do it. I don't know, I might show it later maybe, but it's fine. I think this works well enough. So now we have transformed normals so that they actually face the world direction rather than just the local space mesh direction. So now if I bring back the lighting, so I just go into light frag and bring that back. Now it should look, yeah, okay, there we go. So now we can see the surfaces of the monkey are being lit like we expect them to be. Very cool. So that's diffuse lighting. That's lighting hitting the object directly. Or hitting the surface directly. And next, we're going to talk about something called ambient lighting. So, see you then.